So, continuing with the laser Raman spectroscopy or the Raman effect, I was explaining the Raman effect to you. So, here what happens is, here as you say, it is called a Raman scattering, and this is a scattering part. Now, let us look at the energy level part of it, and let us see how we can explain it through the energy levels. So, here suppose this is the ground level, this part is E0, E0 is called the ground level, and this gives you the energy of each of those levels. Okay. So, here I am talking about a molecule. So, I am talking about vibrational states. Generally these bonds, they start vibrating or rotating, So, everything is on these bonds. Okay. So, they are vibrational levels. So, here I think of another vibrational level here. So, what happens in Rayleigh scattering? Rayleigh scattering means I start off with this red wavelength, it has a energy of h nu 0 suppose. It goes up to a virtual state, again see I come across a virtual state, which is not a real eigenstate at all, but then it manages to go. So, it is not a resonance state either. So, it goes up to this level and then it falls down again. From this virtual state, it comes down to the ground state. It started from the ground state, it comes back to the ground state. So, the energy difference h nu 0 and h nu 0, for both of them the energy difference is the same. So, obviously, the wavelength is the same, and that is called Rayleigh scattering. So, nothing you have not got any idea about the molecule. It started from the ground level, it came back to the ground level. What happened to some other energy states above it, below it, I mean nothing, it gave you no information about that. But what happens again simultaneously is there is Raman scattering, which is an inelastic scattering. Here I say Rayleigh scattering is an elastic scattering. Elastic scattering because no energy less or more, nothing like that has happened. The wavelength has remained the same. See, now I am talking of a single photon, not as a beam of light which has a particular energy. This is a single photon energy. So, everything here is talking about a single photon. So, here there is no change in energy. So, it is called elastic scattering. But in case of Raman scattering, there is a change in energy. So, I start off with the same red wavelength, h nu 0 is the energy difference between this level and this virtual state again. From this virtual state, it falls down, it comes down to this level, which is an excited level really. It is another vibrational state, E 0 plus h nu m. Okay. So, so the difference in energy here is h nu 0 minus nu m, obviously between this virtual state and this state. Okay. And I have got this wavelength, I have detected it with a spectrometer, I have detected it with a CCD camera, we have detected this, okay. And the wavelength is not the same as this. Now, the difference between these two, this and this, gives you some idea about this state. It falls down to this level, okay. So, it gives you nu 0 minus nu m will be this difference. So, you know something about that state of that molecule here, you know something about that. Now, suppose there are some molecules which are already in that excited state of E 0 plus h nu m, and this laser, the red photon goes up. Suppose the energy difference is h nu 0 only, exactly the same as this, but here it is going from the ground level to this level, here it is going to some other virtual level and it goes up here h nu 0, it goes up from an excited state and then it falls down to the ground state. Again it has given you some idea about this vibrational level. How? By just falling down here, and then this energy difference between this and this is equal to this energy difference. So, that is the signature of your molecule. by studying these wavelengths, the pink wavelength and the blue wavelength, you have got some idea about the vibrational levels of this molecule. You know how they are getting excited, what is the movement of these bonds. It is specific to this molecule, because again all these levels depend on the weight of this element, weight of this element, weight of this element. Okay. So, it is specific to that particular molecule. So, it is like a signature of that molecule itself. So, if you were to see it on a detector, what would you see? What would you measure? Here these are the energy level diagrams, no doubt, but what would you see it on a detector? Maybe a CCD detector, after it has it has detected these wavelengths. Now, the central line is the red, which is this, and on this side is V0 minus Vm, that means this pink one, okay, and this blue one corresponds to this line. Okay. So, this is not to scale, no doubt, but it is just a representative of what is happening here. Okay. So, V0 minus Vm, that means a wavelength which is greater than this and a frequency which is lesser than this, lesser than your input laser beam, and this is a frequency which is higher than your input laser beam, but the wavelength is lesser than this input laser beam. So, you get two on your CCD camera or your detector, you see 3 signals. Okay. So, you see 3 signals. Now, you have to decide which one is more important for you. Generally what is seen is this signal is huge. I have just shown it till here. Actually, compared to this is extremely large. Sometimes this is so large and this width is so much that this is hidden completely. Like this becomes like a noise for this. This red thing becomes like a noise for this blue one, and it is lost in this completely. So, you have to do a very accurate experiment in order to just find those two, the pink and the blue signal. Vs, I have talked of it, is called the virtual state. RS is the Rayleigh scattering, RSS is Raman scattering, and RASS is the Raman anti-Stokes scattering. Okay, the one on this side is anti-Stokes, one on this side is Stokes. So, first of all you've got to glean out those 2 small signals, and then only you can interpret it. See, people have done it with ordinary light long ago. They have used sodium lamp or and such things which have only one frequency, and then they have been able to detect that. But it is a very difficult process, it is not so easy. But the moment laser came into the picture, the intensity of this line and this line just increased instantly. The laser intensity is only so much, most of it of course went into this Rayleigh scattering, but then you were able to detect these two very easily with the laser. This intensity went up, so did this intensity, so did this intensity, and as these two intensities went up, you were able to detect them much easily. So, use of lasers for Raman scattering became like a turning point for this technique of Raman scattering. Okay. So, now I just want to show you a schematic of the Raman spectroscopy setup. Okay, before that I think you should know a little bit about this virtual state. Virtual state seems so vague, wonder what it is all about. What is a virtual state? It is not even an exact eigenstate. So, a virtual state is a transient, non-observable energy state. See, it is non-observable, but then we do use it in the theory, state that a system passes through during a quantum process. Unlike real energy states, virtual states are not eigenstates. They exist momentarily during interaction and facilitate transitions between real energy states. The virtual state is not a true energy level of the molecule, but a transient state that allows the molecules to scatter the photon inelastically. The molecule quickly relaxes from the virtual state, emitting photon with lower energy, which becomes the Stokes scattering, or the higher energy, which becomes the anti-Stokes scattering, as compared to the incident photon. Okay. So, basically, if you were to suppose I were not using a red laser, suppose I was using some other wavelength, it could have been a green laser, okay. Visible. Many of these experiments are done with visible lasers, though the energy level to be studied are vibrational levels, those will be in the infrared. So, if it were a green laser in the same molecule, that would have gone up to a different virtual state and come back to either this level or this level or this level. These two levels have remained constant. So, the energy difference nu 0 minus nu m will remain constant. So, you will have an idea of what the molecule, the signature of the molecule, this gives the signature of the molecule. The molecule has remained the same. What you have done is just change the wavelength, the incident wavelength. So, suppose it were a green, the virtual state would have been different, but in reality you are not even interested in the virtual state. It just helps the incident photon to come back to the to some resonant level like this. So, the molecule will give you the same signature of nu 0 minus nu m or nu 0 plus nu m, but your incident photon is green and not red. Okay. So, that is the importance, I suppose, of the explanation of a virtual state. See, if it were an exact eigenstate, then you would not have been able to use a green laser in place of the red for the same molecule. Okay. So, it is a theory explanation which you have to think about little bit and then understand its importance. So, before that, before I go further, let me show you a schematic of a Raman spectroscopy setup. So, here I have the laser, whichever laser you choose. So, say I have chosen a green laser and this is a beam splitter. I put a beam splitter, that means part of the beam can go that side and part of it can come here. So, or it is like a mirror, okay. So, it goes here and it goes here. You take a lens and this is my sample here. You focus your laser onto this part, and now what you have got to do is you have got to collect the scattered light from here and then analyze it. The scattering is taking place here, you have the input beam which has come here, and the scattering is taking place here, and you must take the scattered light here and take it to a spectrometer before you can find the Stokes and the anti-Stokes signal at all. So, you can see it here. What I show in yellow is this, that what is coming out is that you have a large green part of it, which is the Rayleigh scattering. If you had used a red laser, it would have been the red part. You can use a filter to filter out that the incident laser light and take out and let the rest of the thing pass through. In this way, you have sort of reduced the Rayleigh scattering little bit. If you reduce the Rayleigh scattering, then you are able to detect those two small Stokes and anti-Stokes signal on either side of the Rayleigh scattering. So, using a filter just means you are trying to eliminate this part, I do not think you can eliminate the full part, because these also get filtered out. So, you use a certain filter which is specific to this wavelength. So, most of this will go out and these will start showing up. This pink and this blue will start showing up. So, that is the, and then okay, you take it to a spectrometer. The spectrometer will have a grating and multiple lenses and prisms and such to separate out those wavelengths that you are looking for, and then you have a CCD detector to detect its intensity. So, this is a general setup, schematic setup of a Raman spectrometer. Now, what I want to tell you is so this is Raman spectroscopy, but it is called spontaneous Raman spectroscopy. Okay, before I go into the stimulated Raman spectroscopy, let me give you another description of Raman scattering. Okay, so this is like a classical description of Raman scattering. To tell you why Raman scattering occurs at all, why do you get those two Stokes and anti-Stokes signal at all? So, it can be described by this polarizability and induced dipole moment. So, this you have come across before. I have spoken in some other lecture when I started off with non-linear optics. So, whenever I have an electric field, an external electric field, it creates a disturbance in those in the molecules or in the atoms which constitute that material. So, the plus and the minus sign, because of the nucleus and say the revolving electrons, they slightly get displaced. Just try to recollect that. So, the explanation is similar, and external electric field E, incident light interacts with the molecule, inducing a dipole moment P. Okay. So, P is equal to alpha E. Obviously, P is that polarization, okay, dipole moment. I will not call it polarization, because remember, though I am using the factor P, which I have described earlier as polarization, which is dipole moment per unit volume, but I am not taking the unit volume. Okay. So, P is the dipole moment. So, P is the dipole moment is will be equal to alpha E. So, it is proportional to E, and alpha is the polarizability. It is called a factor polarizability. It is a tensor. So, it is different in different directions, okay, in that material. Whatever the material may be a gas, it can be a liquid, it can be an actual solid crystal. So, consider a liquid or a gas phase in which this polarization, a polarizability tensor of the molecule, and alpha represents how. So, alpha, the polarizability, represents how easily the electron cloud of molecule is distorted by the electric field. You know the electron cloud is getting distorted, but how much is the distortion? That is the idea. So, when there is an external electric field from an intense laser beam, the electric field associated with that light beam, there is a distortion in your electron cloud that is known, which gives rise to the polarizability. So, alpha is a value which tells you how much is it distorted. It gives you some exact way of describing the distortion. Cloud of the molecule is distorted by the electric field. For Raman scattering to occur, the polarizability must change as the molecule vibrates. So, the molecule will start vibrating when it is absorbing certain energy, which is from the laser light. Okay, it starts vibrating, and at the same time the laser light has this electric field associated with it, and because of that electric field also it starts vibrating, it moves. Okay. So, there is a change in the polarizability. If the molecule undergoes normal vibrational mode of frequency nu v, the polarizability with time and coordinate will change. So, that is easy to understand. So, if it is vibrating, so obviously your coordinates of those electrons is changing, and at the same time over time also it is changing. Okay. It is changing in time and it is changing in coordinate because of the vibration. Okay. So, alpha can be given as alpha 0 plus d alpha by dx x. Alpha 0 is the equilibrium polarizability. Okay. It is the equilibrium part, there is no vibration till then, and d alpha by dx is the rate of change of polarizability with the vibrational displacement. So, it has taken some energy from the laser and starts vibrating, and that brings in the displacement, it keeps on vibrating. So, the alpha is also changing. If such a thing happens, then only your Raman scattering can occur. Since the molecular vibrations follow simple harmonic motion, so I can write x is equal to x 0 cos 2 pi nu v t. Okay, this is the solution to the simple harmonic motion. One can write it as this. The polarizability of the oscillator, if I substitute this into this, is given by this, where alpha dash is this part. Okay. So, this is also polarizability is also changing over time and over coordinate. The incident electric field of light, as you know, is given by this, because it has a particular wavelength or frequency nu 0. Just see the distinction, this is the vibrating mode of that molecule which is given as nu v, while this is the frequency of the light. Okay, nu 0. So, that is the distinction between nu v and nu 0. Okay, so, substitute again into p is equal to alpha e, and you can just do all this. Just substitute it, and it is very easy, and then use a trigonometric identity which is of this kind, cos a cos b is equal to half cos a minus b and cos a plus b. Just substitute all that here, and then by expanding you just put this, what happens to the dipole moment p? P is equal to alpha 0 E 0. When you have done all those substitutions, this is the final equation. Now, how many vibrations does it have? Alpha 0 E 0 cos 2 pi nu 0 t. So, this is like the incident field itself. So, this corresponds to the Rayleigh scattering, where nu 0 was the incident frequency and it remains as nu 0. So, this part of the equation is the Rayleigh scattering. Now, see the next part. Next part has a cos 2 pi nu 0 by minus nu v. That corresponds to the Stokes Raman scattering. So, this is a new frequency, this is different from this frequency. Okay. This is a new frequency, and you get nu minus nu v. Then you have one more frequency nu 0 plus nu v. Okay. So, you have 2 new frequencies. So, even by this classical method of explanation, this is a classical method. What was done before, this is the quantum mechanical method. Okay. And this what I have given here is the classical method. Both of them are giving you the same results. Okay. They are just 2 different explanations of Raman scattering. Okay. Now what has happened? Now see, before the lasers were invented, the Raman signal or the Stokes Raman signal, between Stokes and anti-Stokes, I think I should tell you this. Okay. The anti-Stokes signal is always so tiny, the Stokes signal is always larger. That is because you will find most of the molecules in the ground level and very few molecules in the excited level, from where it has to excite again and de-excite. So, the number of molecules here is less, the number of molecules here is more. So, obviously, this signal is more and this signal is less. So, that is the difference between Stokes and anti-Stokes, why this signal is more and why this signal is less. Now, with the advent of lasers, as I said, the Stokes signal goes up, increases, because lasers itself have such an high intensity. But then still it is not so easy to detect, it is very difficult to detect. How should I increase the intensity of the Stokes signal? So, people have found out one way. I will not describe in detail, but you can understand the concept very easily. It is called stimulated Raman scattering. So, all this what I had described till now is called spontaneous Raman scattering. That means, you have a laser light and spontaneously it gets scattered in a particular direction in a particular way. Spontaneously it happens. But you can stimulate the similar quantum effect, but you can stimulate it. So, let us see how that can be done. So, in stimulated Raman scattering, intense laser field enhance the Raman signal significantly. Okay, so, why did people go in for a stimulated Raman scattering? They went in for that because they wanted to increase the intensity of the Stokes signal. This is the Stokes, this is the anti-Stokes, and this anyway is the relay. So, this signal anyways got intensified because of the use of lasers, that is one, but you wanted to increase this intensity even more. Then you shifted from Raman scattering to stimulated Raman scattering, where this intensity will go up in stimulated Raman scattering. Okay. So, stimulated Raman scattering is not very much different from this, only thing is you have this bottom state and this is the vibrational state and this is the virtual state. So, what we have done till now is put a laser there and the same thing comes down here with a shifted wavelength. So, this part is called the Raman shift. Or nu 0 minus nu v is called the Raman shift, nu 0 plus nu v is called the Raman shift. Okay. So, that is the nomenclature. So, here I have this is the spontaneous. Now, how do I make it stimulated? See, I have only input this wavelength or this frequency, this has come down on its own. There is a nu m which was on its own, it has come down. Now, what people have done is, what they have done is they have taken this wavelength, they have used a laser for this wavelength, and this wavelength also they have taken another laser which they can keep on tuning. So, suppose nu 0 is constant wavelength. So, you have your sample say here. So, you have one wavelength which is given by frequency nu 0 and you have one more wavelength which is called nu Stokes maybe, and you are not sure how much this is, and your whole aim is to find this difference in any case. So, you take a tunable laser for this Stokes and you keep tuning it. The moment this frequency is matched, you will get a signal. This is what is stimulated. You actually stimulated the virtual state to give up its energy and come down here. Not the virtual state, the molecule which is in the virtual state. You stimulated it at a particular wavelength and made it to come down. So, nu m was no longer spontaneous, you were generating it here. Okay, so, that is the difference between, and you have done it because you wanted an increased signal. this increased signal. Quite often this process, stimulated Raman scattering, involves 3 interacting fields. Okay. So, 3 interacting fields means this, this frequency or this energy level, this energy plus this difference in energy here. So, there are 3 fields, 3 fields. That is why it is a third order nonlinear effect. Quite often Raman scattering is called a third order nonlinear effect. If you remember the polarization, here I will call it P dash because you will confuse between P, which is the dipole moment, and P is the polarization, is proportional to chi3 E cube. So, there are 3 fields, it all need not be the same. So, 1, 2, 3, there are 3 fields, and that is influencing the polarization. That is why it is a chi3 effect. That is why it is a third order nonlinear effect. And a third order nonlinear effect, as I have said before, third order nonlinearity, it is a very weak effect. But still, you can see it because you have those 3 frequencies and you have gone into the stimulated Raman scattering. Okay. So, you must remember that Raman scattering gives you a signature of the molecule or the atom or some other molecule in the liquid phase, in the gas phase. It is kind of a signature of that particular molecule, and you are trying to track the vibrational levels of that molecule. Okay. And you need a tunable laser. So, here is in Raman spectroscopy, in stimulated Raman spectroscopy, you need spontaneous and stimulated, you need a tunable laser. Dye laser will come in very handy because you have lots of colors which can be used.